For 2 years, Diane Katz lived in a state of persistent unresponsiveness. She was unable to speak, track movement with her eyes, or acknowledge her family. Doctors administered half a tablet of the sedative zolpidem. At the 20-minute mark, her physiological state shifted. Her eyes began to focus and track movement across the room. Shortly after, Diane sat up independently, kissed her mother, and spoke her first words in years. This recovery presents a specific systems engineering problem. A drug designed to suppress the central nervous system for sleep had somehow enabled a dormant brain to engage. This points to a condition called signal saturation. The hardware is intact, but the internal noise floor has hit the system's voltage ceiling. The sedative acts as a signal pad. Suppressing the static creates headroom for inherent signals to emerge from the noise. Many neuroinflammatory states follow this logic. The system remains operational, but the circuit is latched into an attack state that effectively jams normal processing. Linda, a 52-year-old stroke survivor, lived for 3 years with severe speech impairment and physical paralysis. Standard therapy had reached its limit, leaving her in a state of chronic cognitive fog. While traditional neurology assumes pathways are destroyed by a stroke, this model suggests many logic modules are simply dormant. A stroke triggers a chronic inflammatory response, flooding the neurovascular unit with a molecule called TNF-alpha. In this system, TNF-alpha functions as the master gain knob. High levels crank the brain's sensitivity to a maximum, forcing signals into a state of continuous distortion and failure. When Linda received a perispinal injection of etanercept, her speech became crisp and her mobility returned within minutes. The drug serves as a rapid heatsink. By neutralizing the TNF-alpha, it instantly lowers the systemic gain and allows dormant pathways to fire clearly. Removing the inflammatory noise jamming the system demonstrates that functional restoration is possible through targeted gain adjustment. Charlie, an Alzheimer's patient, had reached a stage where he could no longer recall his career or identify his own grandchildren. Doctors applied the same gain reduction strategy. They administered the TNF-alpha heatsink to determine if clearing the noise could restore technical memory. Following the injection, Charlie's cognitive fog lifted. He was able to fluidly recount his technical history as a machinist at the Livermore lab. He specifically recalled building and fixing the components for the Hubble Space Telescope, a highly complex memory previously buried under internal static. Alzheimer's patients often exhibit TNF levels 25 times higher than normal. Reducing this protein directly correlates with the clearing of cognitive fog. While these results are immediate, they reveal a critical engineering challenge. Consider the duration of these pharmacological interventions. If the sedative effects fade in hours and the injection requires constant repetition, the goal shifts to maintaining a low noise floor through sustained metabolic calibration. Sustaining these results requires a hardware calibration framework, a systems engineering method designed to stabilize the brain's internal environment. We model the neurovascular unit as a CPU triad: microglial security drones, astrocyte cooling systems, and neural wiring must all be optimized to achieve laminar flow. To address signal saturation sustainably, inositol is used as a metabolic current limiter. It acts as a permanent signal pad to prevent voltage surges at the cellular level. The technical stack employs NAC and rutin to function as a systemic heatsink. Together, they neutralize oxidative stress and directly suppress the TNF-alpha gain knob. Choline is then introduced to refurbish the brain's dielectric insulation. This thickens the myelin sheath to prevent the signal bleed and crosstalk that characterize a noisy processor. Lowering the noise floor allows the microglial security logic to switch from an attack state to a maintenance state. Only then can they begin pruning the unoptimized wiring known as a rat's nest. Systemic gain adjustment reveals that function often persists beneath a layer of signal saturation. By stabilizing the hardware environment, we move the brain from a state of emergency failure back into dynamic equilibrium.